It's a real pleasure to be here and help celebrate IDSS and the accomplishments. So I was here from 88 to 98 and happy, but I left because there wasn't any statistics and it was kind of clear there wasn't going to be any. In fact, to your shock, you may not know that there was no really machine learning. Machine learning was not viewed as a part of computer science. That was really surprising to me. It was clear it was going to happen, and it wasn't happening here. So I left, not unhappy, but just felt I needed to learn new things. And I watched all the committees form around circa 2000, and I kept hoping, something would go somewhere. And I remember meeting with Mike Sipser in Au Bon Pain, 2010 circa. And he sat down and says, I'm behind this. I'm not a statistician. I'm not sure I get it, but I believe in it. And I thought, wow, Mike Sipser says that. And I've recruited Munzer Dali to lead it. And I said, okay, it's really going to happen. And it did. So I need a little help. I got Munzer's talk up here, so someone's going to have to put up my talk. I could give Munzer's talk. I love his triangle. I could just talk about that the entire time. Okay, you got to go back to the beginning of the talk. That's the end. All right. Okay, now you got to do something else. And someone in the back. All right, we made it. All right. Okay, so the learning is in the title, and mechanism design. So what I became after I decided to be a statistician, which took about 20 years, is trying to become an economist, and that's still ongoing. And I'll try to tell you why. Now, I admired Munzer's introduction for many, many reasons. First of all, I totally resonate to the entire sort of scope, and the fact that he never said the buzzword AI the entire time was amazing to me. It is an elephant in the room because it is still dominant at MIT. It is often viewed as supplanting statistics, and that point of view is not true on the West Coast, I can guarantee you, but it is still true other places, in particular in industry. So I want to address that elephant in the room to start here. I do want to say something about what AI was. So first of all, when I was here, I was in E10, which was a building here before this building was here, so I was right down there. And Minsky was somehow right up there. And so I knew about AI, and I just didn't like it. And I want to kind of finally, after all these years, say why. Okay, so what I think AI is in this era, what we read about in the newspaper and all that, is really a new engineering field that's emerging, okay? Most engineering fields emerged because there was some science, some fundamental science that was done, and it was kind of clear you could use that to build new things, and it was kind of clear it was not clear how to do it. So we had quantum chemistry, fluid mechanics, and so on in circa 1920, 30. There wasn't a field called chemical engineering yet. Okay, but people started to build big factories that says, if we know what happens when we put molecules together in a test tube, maybe we could even do that at huge scales. And of course they tried, and it sort of worked and often didn't work. It often either exploded and killed people, or it actually didn't deliver product and was not economically viable, but occasionally it would work. And then principles started to get worked out, and they weren't just the same old principles. New thermodynamics, new ways of putting things together, new differential equations emerged, and so on. It became a mathematical field of its own. Electrical engineering I know less about. I actually studied some of the chemical engineering history, very interesting, very worthwhile. Electrical engineering, there was already Maxwell's equations before you had electrical engineering, so there's kind of a full understanding of the phenomenon at some level. But the idea of electrifying a city or bringing power into a home and having it not burn down, or building circuits, or doing communications was not there, and that had to be developed, okay? So those were brand new engineering fields that brought vast value to human beings, and of course there was civil and mechanical and so on, all right? Now, statistics, has often viewed its goal as not engineering so much as science, supporting scientists in discovery, and that's great. But there's this gap, which is that is there an engineering version of that? All right, and I think that's what machine learning is, and I think what we're seeing rolled out in society at large, on the basis of the networks and the flows and the data and all that, is a new engineering field, and it's the first engineering field that has humans as part of the stuff. It's not just about atoms in the world and chemicals and so on. It's about humans and data and all that put together. So it's a very challenging engineering discipline. And calling it AI ruins it, as far as I'm concerned. It warps the way we think about it. All right, so this perspective that I do associate with people like Minsky, to very much cartoonize it, was somehow that let's understand intelligence. We can do that. And if we understand that, all these great things will flow from that. And that is still, to this day, DeepMind's sort of mantra is understand intelligence first, and then solve all problems. Chemical engineers didn't sit down and say, let's build an artificial chemist and they will solve chemistry problems for us. That's not what a chemical factory is. Okay? We don't know what intelligence is. With all due respect to Sebastian Bubeck and all, we may have some glimmers of something, right? And I'm fine to call it some notion of intelligence, but it's not the kind I'm really interested in. It's not the kind I think is going to be the most impactful in human society. The other aspect of the AI dream was that it had to be autonomous. It had to be intelligent, whatever that means, and it had to be autonomous, because it had to look like us. If it's autonomous, it's not tethered to us, therefore it must be intelligent. So for many, many decades, it's been kind of an unquestioned goal that it has to be autonomous. And definitely there are use cases, robots in burning buildings and so on, you want it to be autonomous. But most good systems don't have autonomous nodes. Planes flying through the air are not autonomous, right? It all should be federated in networks. So this audience doesn't need to hear that, but other parts of campus need to hear that. The goal should not be autonomy. Autonomous self-driving cars is ridiculous. I do have opinions still to this day. All right, so here's a different point of view on intelligence, and it's not that unfamiliar. It should be about the collective. That's the level of analysis. It shouldn't be about the individual. So economists think this way, even physicists think this way. But if we think about it from an engineering point of view, thinking about the collective gives us kind of new things to think about. What kind of collectives? They're going to have now computers in their midst. Maybe new things will happen, not just old collectives, but new kinds of collectives will emerge. It's not just that we throw super intelligence in there and great things happen. It's that we think about what should be the goals. That's what a good engineering field does. All right? So autonomy and mimicry are leading to this, look, Ma, no hands, it works, and wow, isn't it wonderful? Now, I am caricaturizing, but not so much. There's just not an articulation of the goals of AI to this day. All right? Autonomy has many attendant dangers, the one I alluded to, kind of not well controlled, but also it concentrates the efforts in small numbers of people. A company like OpenAI has got to develop the product, because if everybody develops it, like Wikipedia or something, it's not intelligent. It's just humans did it. If it's autonomous, it looks like it's super intelligent. So that's now concentrating things in small numbers of people. And I don't like that. I don't think that it was good for search to get concentrated inside of Google. And we're reaping the negative effects of that to this day. All right, so now there's also the thought that there should be new kinds of collectives, and I'm not quite sure what they are. But I talked to my spouse the other day, and she says, well, what about like intelligent migration? What would that look like? Interesting thought. That's a collective phenomenon that may emerge. Maybe we can think about that in a smart way. It doesn't, swarms, and we talk about ants being intelligent, that's very, very limited. I do think that's true, but we should be more aspirational of that. And I think that we're not being aspirational enough. Now, you do have machine learning people and AI people talking about alternative paradigms. This is the federated learning one. Let's say, oh yeah, it shouldn't be all centralized. It should be federated, and there should be all these edge devices. But the model of federated learning is that there's a centralized place that takes in everybody's data, all right? And it, in its glory, makes a big model that sends to everybody, and they're all happy, all right? There's no economics in this picture. That's really what's wrong with this picture, okay? Those things at the edge are people, typically. They have things they care about. They have values. They may or may want to participate in your game. They want to be part of the system, and in fact, the focus should be more on them. They will value their data. They want to get benefits out of it. And so minimally, we start to have to use the language of economics. What are the trade-offs? What are the values? What happens when you bring them together? What's the overall welfare of the system? Right? Now, my talk's going to be a lot about economics. It's not the case that just economics solves the problems either. But there's going to be my version of a triangle. And this is the academic one. I think the phenomenon is actually a real-world one. This is an emerging engineering field in the real world. But as an academic, what should we be doing? And I certainly have been a bridge between statistics and computer science, and I think that's all machine learning is. It's nothing new. All the ideas are already sitting there in Blackwell and so on in the 50s. They've been deepened in various ways, but they are not new, all right? But bringing in the computer science perspective is turbocharged it. So that's great. That's machine learning. Of course, statistics meets economics, that's econometrics. But econometrics has been limited. It's more about measuring the economy and less about designing the mechanism design. Mechanism design is its own field. In fact, economics mechanism design part of it kind of meets up to computer science in something called algorithmic game theory. Algorithmic game theory has no statistics in it. So you can sort of see this triad. There's lots of dyadic connections historically that are really important and powerful, but there's no triadic one. Okay, now again, IDSS and Munster's triangle suggests that it is here and it is latent in many other places as well. The fact is, in the real world, all three of those things are present. I spend a day a week at Amazon. I can assure you, to solve any problem, you have to have all three of those communities. And of course, applied math, control theory, et cetera. This is not meant to be exclusive in any way. It just highlights some connections. The other thing I do is I spend time in the real world and I really work on emerging markets. Because I don't think it's about, I think it is about the collective. All right, so here's just to give an example of one that I'm involved in. Music has been prey to the mentality of centralization. People put music out there all the time, more than ever before in history, by a factor of 100. And people listen to music by a factor of 1,000. And so you might think there's brand new jobs have been created. And basically, no. There's a few people who are still getting rich, but there's all the people who are actually making the music that real people are listening to are not getting paid. Because it's all been put on a centralized platform and then streamed, and then there's some kind of a subscription or advertising model. All right, so how do you fix that? Well, you think about it in terms of a multi-way market, not in terms of a streaming platform that you have to monetize with advertising or subscription. So United Masters does this, and this is a friend of mine, Steve Stout, a brilliant entrepreneur who has created this company and other companies. Basically, there's 2 million musicians on this right now. They did not sign with record companies. They are some of the emerging great musicians. And we first set out to build a two-way market between them and their listeners. So they got to know who was listening to them. They were able to advertise their shows. They were able to start to make some income just based on seeing who they are connected to, selling things, and so on. Then Steve made that into a three-way market by signing up the NBA and FIFA and other entities, brands like that. If you go to the NBA website now and you watch a clip and there's music behind it, that's actually streamed from United Masters artists. So a 16-year-old probably made that music. It's not Beyonce anymore. It used to be, and they would pay Beyonce's record company. Now the money goes to the artist as part of a market. It's not just a handout, it's part of their market. The artist then starts to monetize that themselves. They start to say, oh, I'm connected to the NBA. Maybe Nike would be interested in me too, and that's happening as well. So that's just the glimmerings of, to me, intelligence. That's the glimmerings of something that's real in human life, that's not existing, that's missing. And in the economics language, money's being left on the table. Human happiness is being left on the table. The ability to have a job as a 20-year-old for making really good music that lots of people are listening to has not existed. And now it exists, right? So in some ways minimal, but I think this is what we should be doing more of, thinking about things like that. Okay, so as a academic researcher as well, I think a lot about what are the challenges, and most of these are not new in any way. These are what I've been doing the last 10 years. But again, people like David Blackwell and Kolmogorov and von Neumann and all were doing all these things. They didn't see these fields as separate, and they were statisticians and mathematicians and computational people and control theorists and so on. All right, so in machine learning, we know a lot about the dynamics of approaching optima. In non-convex problem with saddle points, blah, 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 there's some experts in the room, a lot of us have worked on this. But economic situations, you rarely approach optima, you approach equilibria. Equilibria have very different properties. You need fixed point dynamics. Dynamics like gradient descent will fail when you try to approach equilibria and so on. And again, there are people in the room that work on this. I've been very interested in this. That's ongoing. Stochastic versions of, extra gradient and so on are all kind of the rage these days. Incentives brought together with exploration and exploitation. Those three words rarely appear together in any paper or any talk, but they are crucially important. You can incentivize exploration, you can incentivize exploitation, and you should do this in the context of these multi-way markets I talked about. I will talk about information asymmetries in contracts. Uncertainty quantification is behind all of this stuff. If you don't quantify your uncertainty, you can't make good decisions, and you can't make good decisions in a market context. And we don't have good methods for uncertainty quantification. It's an elephant in the room for all of the machine learning AI people. Their black boxes output things which are not calibrated, and they are often hugely biased, and they don't even know. So as a statistician, that's problematic, but also a wonderful challenge. Calibrating and then mechanism design with learned preference. So I'm going to focus on 2 of these. I think the last time I was at this conference, I did like 3 of the other ones, but I'm going to focus on 2 that are much more recent. One of them has a lot of economics in it. I'll start with that, and the other one is more of a statistics focus. Okay, this is the one that has a lot of economics in it. All right, so with colleagues Stephen Bates, Michael Sklar, and Jake Soloff. Stephen's a postdoc with me at Berkeley, brilliant young statistician. Michael's at Stanford, and Jake was a grad student who's now moved to Chicago. All right, so contract theory is one branch of theory of incentives. The more well-known branch is auction theory and matching markets, but contracts is a venerable old branch. It's a asymmetric version of economics, of really a mechanism design. A lot of economics is more symmetric. You get curves that cross, and you have players in a Nash equilibrium and so on. This is Stackelberg. This is asymmetric. And it's Stackelberg with information that's not shared, which is not known. Okay, so it's sort of a Bayesian Stackelberg, if you will. So I have a principal who wants to incentivize an agent to do something. I'd like Martin Wainwright to do something. Martin knows a lot more than me about certain things. I don't know that, so I can't do it. But I don't know exactly how much he knows. So I can't just ask him and say, I'll pay you as a function of how much you know. Martin, how much do you know? He'll tell me I know a lot. He'll lie to me. And I'll overpay him. So he's incentivized to do that. That's part of the system. All right, so I'm going to be more clever about that, and I'm going to offer him some options. If you do this, I'll pay you this amount. If you do this, I'll pay you this amount. A menu of options. That's what contract theory focuses on. It's not just a price. It's not a posted price. It's a menu of options. And you all know this from the airlines. There's not one price for every seat in the airplane. And you probably have thought about it a little bit and why. Well, obviously, there are a few people that are willing to pay a lot. If you give them a low price, you lose all that possible surplus. But if you try to identify who those people are, you're doing price discrimination, it probably will be illegal and it probably won't work. People will fake being not willing to pay so much. If instead you lower your price a lot, you'll have lost that, but you'll get a lot of other people on the airplane and so on and so forth. So instead, you carefully work out the service level and the price so that people will self-select. And it's non-trivial, and there's mathematical equations for it. That's what contract theorists do. They had a huge impact on the airline industry. All right? It's amazing how just a little bit of extra service, a little bit of red wine and being first in line, there are people who are willing to pay $1,000 more for that. It's amazing, shocking. And they feel so good about themselves. You see them, there are other people that say, my gosh, I'm so happy to pay only $100 instead of $1,000, and I don't care about that stupid glass of red wine, and I don't care about being first in line. They feel good about themselves too. Social welfare is high, and the airplane is full, so revenue is high. That's what contract theorists do, and they've had trillions of dollars of impact by doing things like that. Now, on the other hand, as I alluded to in the little triangle, they don't do statistics. All of their designs are based on assuming the distributions are known a priori. Wow. Okay, in the modern world, that's just a non-starter, and it's way inefficient. All right, now they call themselves Bayesian, which is kind of interesting. So you'd think that they were statisticians, and I've sort of said this, the contract theory doesn't have much statistics or any in it. And they say, of course, we're Bayesian. And you say, okay, I see there's a probability distribution there, and there's an expectation there. But that probability distribution, that's the prior. And you're just taking an expectation over the prior, and you never update the prior. That's pretty limited Bayesian in my view. So we have a great opportunity here to work on this problem. All right, so let's make this concrete. As you all know, clinical trials run every year, and it costs tens of millions of dollars per disease, basically. And they're hugely important. The vaccines would not have happened if the protocols had not been worked out for clinical trials. Immense social investment. It's clearly a statistics problem, but it's also a information asymmetry problem. The FDA's job is to run the clinical trial, so they're trying to control false positives and false negatives, type 1, type 2 errors. And they do. They're really good statisticians there. And they use the latest classification technology and all to do that. All right? On the other hand, which drugs do they test? They don't figure out which drugs to test. They're not being scientists. They get the drug companies to send them candidate drugs. And now the drug companies know more than the FDA about the particular drug. So they may have done some internal testing. They may have put their best engineer on it. They may know something. They'll know things about it. All right? The FDA is trying to figure out how many people to run in this clinical trial, how much expense to pay, what's the risk, and so on. They could just ask the drug company, what do you think for that drug you're about ready to send me? How risky is it? How likely should it be licensed? I'm going to sit over there, I'm going to lie. I'm going to say, it's a really wonderful drug. You should definitely go to the market. So the incentives are wrong, and that in fact leads to bad behavior. And you see this all the time. The FDA is aware of this. Here's a typical type 1, type 2 error control test for the FDA. It's Neyman Pearson. False positive probability is 0.05, false negative is 0.2, kind of typical numbers. Here, a bad drug means not a drug that hurts people. They definitely screen for that, but a drug that just doesn't do anything. There are tons of such drugs out there. The company that is sending that up doesn't know that it's a bad drug. They may suspect it is, but they send it anyway, hoping for a false positive. It'll be approved. They'll make some amount of money for some amount of time until some other drug that comes onto the market. And that happens all the time. So let's think this through a minute. This protocol is an optimal protocol from a statistical point of view, but it's not an optimal point of view from an econ statistics point of view. Suppose that we're in a case where there's small profit to be made. So it costs $20 million to run the trial, $200 million if approved, kind of a typical for a very small drug. I, the CEO, and the FDA can both do a calculation. We don't know if theta is equal to 0 or not, but we can condition on it counterfactually and compute the expected profit, and in this setting, it's minus 10 million. So the CEO is now incentivized to not send the candidates up there unless they're really pretty convinced it's a good drug. So now the FDA is very happy. Mostly they're getting good drug candidates, and they then test them and so on. What if it costs $20 million to run a trial and you make $2 billion if approved? That would be more like ibuprofen or something like that. Here, if you do the same calculation, the expected profit, if the drug were actually bad, it would be 80 million. So the CEO is very incentivized to send tons of such candidates to the FDA, hoping the FDA will screen them effectively. But the FDA has a type 1, type 2 error control problem, and they make lots of false positives. Okay, so I hope you see this is a contract theory problem. We have a principal and we have an agent. We have information asymmetries. What's new here is that we have a statistical test in the middle of that. Okay, our contract will have service, price, and outcome of statistical test. And the goal is not just to kind of calculate some expected value. The goal is to make sure that overall type 1, type 2 error of the whole system with incentives is controlled. So incentive compatibility meets type 1, type 2 error control. So long story short, I don't want to get into details in this talk, but we have written now several papers, and we're in the middle of writing several more that develop a thing we're calling statistical contract theory. And so just roughly what it is, the agent has private information, their type. There's a protocol which they pay some kind of a pay-to-play price, a reservation price R. If they opt in, if they could just walk away, that's fine. But if they opt in, they pay that. They choose a payout function from a menu. I'll say a little bit about what that payout function looks like, but it's kind of like service price. Then there's a statistical trial, so this is what's new, that comes from a distribution that's indexed by this type. All right. Having gotten that, the agent then receives a payoff indexed by that random variable. The principal gets a utility indexed by that random variable and the true type, because the FDA over the years will sort of pay for it, look bad if they approve too many bad drugs. Okay, so that's the setup. And the agent is doing best response in this setting, and then we work out kind of what does the incentives look like in this setting. So this slide's kind of a little bit busy, but it's just really, really simple. You have to, if you're going to do statistics meets economics, mechanism design, the first thing is what are the incentives, and are we incentive aligned, incentive compatible? And so we just wrote down incentive compatibility conditions. It should be the case that the agent's expected profit is less than or equal to 0, and that is the expected profit under the null condition. So this is kind of a null hypothesis condition for incentive aligned. All right, so you write those down, and all right, and then you sort of say, okay, now how are we going to gather statistical evidence here? Are we going to get p-values, or what are we going to do? It's Neyman Pearson, but maybe it's a little different. And the short answer is that you don't use p-values, you use something else called e-values. And I don't know if again, the audience is maybe not yet statistical enough to know, but e-values are an alternative to p-values, where a p-value is a tail probability under the null. An e-value is the expectation is a random variable whose expectation is less than or equal to 1 under the null. Okay, so if you know a little bit of martingales, this looks like kind of a super martingale. And that's the bigger picture. So these are super martingales that are bounded below. And so we have a theorem that says that a contract is incentive aligned if all the payoff functions are A values, if and only if. So it's actually a characterization of contracts. And we have a further characterization of optimal contracts under revenue. Okay, so that's kind of a neat connection between core economic concept of incentive aligned in a contract and how to gather statistical evidence, which are E-values, which have been developed for completely different purposes. We now have, so I'm not going to get into the mathematical theory, but we have a paper that goes through it in all the gory detail. There are some interesting applications emerging for this, and one of them is this domain of federated learning. So again, federated learning is mostly about Googles and et cetera, gathering data up and worrying about the compression issues and the privacy issue and all that. Again, no economics is involved. But I hope you can sort of see this as a natural fit here. If you think about this as a principal-agent problem, the principal wants to get the agent to do something, which is gather data and maybe gather high-quality data. And the agent knows how much it costs them locally to gather the data and how high quality there is. So there's totally an information asymmetry. And there is an overall contract you can write for this. All right, and so we have a paper that's from last year on incentivizing data sharing and federated learning. And again, we have several other papers en route. This is a big topic for us. Well, so you can tell me how much more time I have so I can calibrate here. I did, sorry, 15 after? 20 minutes, okay, I got plenty of time. Okay, so I'm going to move on. That was a piece of work that brings together statistics with incentive theory. I think this is going to, a lot of people are going to be working on this. A lot of people already are. It's not completely empty of people. But the main area where incentives have come back together with learning has been auctions. So there are big literatures on that, learning of auctions. And that's great, but auctions are this symmetric situation, and they're more kind of like for the Googles of the world trying to make money by having these symmetric players, fight it out, like advertising markets. I think this one is more human. I think that this principal agent paradigm, it really fits lots of situations. Information is distributed, we all know that, and information does not necessarily just want to flow, right? Information only wants to flow if the incentives are aligned. Right, and once the incentives are aligned, then good things can start to happen, and you can let the little player have leverage, and the big player has to pay some information rent. And we want to characterize all that in statistical terms. That's been done in Bayesian quote-unquote terms, but not statistical. So for the younger people in the room, I want to encourage you. I think this is a real opportunity to get engaged in something that's just starting. All right, this part of the talk is more about statistics and kind of the counterpoint of statistics with all the predictive machine learning we're seeing. Okay, so in some sense, the predictive machine learning we're seeing is just statistics. I totally believe that. It's non-parametric statistics. It's gradient descent, for God's sake. It has wonderful, interesting properties, and those should be studied and all that. But it is just statistics. And as a statistician, you look at a predictive model, you say, yes, but. It makes predictions, but maybe those predictions are just not so good, or maybe for some purpose, they make the wrong decision. And should I not worry about that? So the talk I gave here the last time, several years ago now, was on uncertainty quantification and conformal prediction, and that is becoming a thing. So controlling the size of the confidence interval has become a thing. Even if the predicting engine you really don't know much about, a black box prediction can lead to quantifiable confidence intervals. So that's great. But the remaining topic is the bias. Okay. We worried a lot in statistics about variance. That's usually the thing we have to worry the most about, and we're kind of mostly unbiased or close to unbiased. But in this new world, we're going to be hugely biased. I'm going to show you empirical examples. I hope will convince you of that. You all know that we have these predictive engines now. So, for example, predicting the 3D structure of a protein is, let's not call it solved, but it's a huge jump in accuracies. And many other areas of science are being changed by the availability of these predictive engines, and that's definitely cascading and continuing on. Now the scale is interestingly is wildly off in some ways. There are hundreds of millions of amino acid sequences whose structures have been predicted by AlphaFold, hundreds of millions. Right? There are hundreds of thousands of amino acid sequences whose structure is known crystallographically. Okay, so it's a huge imbalance, and it's only going to continue as these things kind of feed back on themselves in positive feedback loops. Is that good or bad? Well, I'm not going to, I think it's probably overall good, but we got to worry about how we do this. In particular, you're starting to see papers now that will study a phenomenon in biology using the predictions from AlphaFold as the raw data. Okay, so here's a paper, it's a good paper, I'll just say, that studied originally this problem, very interesting problem of protein phosphorylation and intrinsic disorder. So some proteins have regions in which the quantum mechanics is strong enough that you actually see intrinsic disorder, and that was kind of viewed as a fun phenomenon for a long, long time. It's now realized that's actually a real signal inside of the DNA, and phosphorylation is somehow connected to that, and so it's a real signaling pathway to be disordered. And so there's now, large interest in this. In 2004, when this paper first appeared, there just was not enough structures to actually test this. Okay, so you could not do a statistical test on that. All right, but now with all the AlphaFold predictions, we've got 200 million, structures. They're not real structures, but they're predictions. They're pretty good. The accuracy really is high. The machine learning, accuracy is very high. All right. That's great. So now you have a paper then in 2022 that comes out and says we're going to actually assess that old prediction. We're going to do an odds ratio, a hypothesis test, between association or non-association of these two phenomena. And the interesting fact is their analysis only used the predictions from AlphaFold. No data was used. Okay, it still might be correct. It's just, that's a little worrying. And that's going to happen surely more and more. All right, so they replaced in their odds ratio the probability of intrinsically disordered region given phosphorylation. That odds ratio, they just replaced the IDRs with predicted IDRs and went on their merry way. All right, so you probably have other examples of this. Here's some of the ones that we collected. Access, electricity access, satellite imagery, phenotyping, and so on, all being used with machine learning predictions these days. Okay. Now, AlphaFold does make errors, and it's not hard to find some. Here's one. Okay, that's a pretty serious error right there. Okay, and so I'm going to show you on the next slide, probably the most important slide of the entire talk. We did this with AlphaFold, the entire output of AlphaFold, and I'll just show the slide. All right. So this is that odds ratio I alluded to, the probability of intrinsic disorder given phosphorylation. And we did a huge Monte Carlo simulation. So we have a notion of a true odds ratio in our simulation. That's the dotted line right there. We took the methodology where you just use the predictions of AlphaFold, and we built a confidence interval for that. We got a very, very narrow confidence interval, that little gold region there, showing that it was pretty convinced of its accuracy. The problem is it's not even remotely close to covering the truth. There's no 95% guarantee appropriate for that. It's just wrong, badly wrong. All right, oops. So if you ask a classical statistician in these companies, Genentech or whatever, what will you do there? They say, I'm just going to throw out those predictions. I don't, they're uncalibrated. So they would just use the labeled data, the gold truth, and they do, and they get that gray region. So it is a confidence interval which does cover the truth. The 95% guarantee is being met. But it's huge, right? And moreover, it even includes one. So it includes the null hypothesis that there's no effect. Okay, so those are both really pretty seriously bad answers. We have a new approach we call prediction-powered inference, which is the green thing. And I'm going to be trying to show you how we get the green thing. Okay, so this looks at first glance a little bit like semi-supervised learning, but it's not. You have labeled data, small amounts with XY labels. You also have predictions coming from some prediction engine that someone else perhaps has built. You also have a vast amount of unlabeled data. You don't have the Y primes there, but you do have the predictions still. Okay, so this again looks a little like semi-supervised, but as you'll see, it's not going to be that. Now we have some estimand that we care about. Let's call that theta star. And we'd like to construct a confidence set that's valid for theta star. So okay, we're not trying to make a better prediction. We're not trying to just change the prediction, augment it, or and so on, and improve it in a semi-supervised way. What we want to do is do confidence intervals. So I want a confidence interval, CPP, prediction powered, that contains the truth with a certified probability, 1 minus alpha. All right, so here's the two cartoon approaches. The classical approach would just use only the labeled data. Can't trust this machine learning stuff. it would be valid, but lose power. The imputed approach would wildly treat these labels as gold standard labels and get something which is highly powerful but invalid. Okay, how can we get the best of both worlds? Okay, so again, there's the picture we're trying to aim for. Let me, before I get into show you how we do it, I want to show some other examples. I think the examples are the most fun part of this. So this is electronic voting. We're just trying to estimate the mean, the number of voters for one candidate versus another candidate. This is a particular race that happened in an assembly race in California, in San Francisco. Let me just say this is the code that we wrote to do this. I want to partly emphasize how simple the algorithm I'm about to show you is. It adds that little clip of code there to do the prediction-powered things. Again, you can see that there is an imputed result which is quite far off. This is using a computer vision algorithm to impute, what was the true label. Some of the ballots have been damaged a little bit. Computer vision's pretty good at making a prediction in those cases. So if you throw them in, it'll give you a confidence interval. Problematically, you don't cover the truth, however. And again, we're able to fix that here. You can see the width of the confidence interval with our new approach is much, much smaller than that with the classical for different values of n. Here's a nice example that Anastasios did. I think I showed the pictures and I didn't give the names, but Anastasios Angelopoulos is one of the grad students working on this. An interesting problem in astrophysics is counting spiral galaxies with the new telescopes. And computer vision will make predictions about whether a galaxy is spiral or not. But again, we want to do science. We want to have confidence intervals on these things. Here, the classical approach is probably the better one. The gray, this is different conditions. The gray one is covering the truth, and it's pretty big, but not terribly big. But again, the predictions alone give you a very highly biased result. This is a gene expression problem where we're trying to use transformers, this latest kind of technology, to estimate median gene expression under different promoters, different upstream regions. And again, that picture over there should convince you there's still an issue. There's an issue also here. And I think I got two more examples. California's census, this is just logistic regression with census data using a boosting model. You can see the imputed result is terribly off. And then last example is my favorite one. This is Clara Fanjang, who works on many kind of applied stat problems, including plankton counting. So if you go out into the ocean, you like to assess the health of the ocean. One thing you do is try to decide how much plankton there is versus detritus. So that's detritus and that's plankton. And it's time-consuming to do this. Computer vision algorithms have been developed, and of course they may have some errors. So you do the same kind of thing, and again, you get errors here, and in fact, it's only the prediction-powered inference one which gives you coverage of the truth. Okay. All right, so let me give you a little flavor of how this is being done, and I'm going to show you a derivation on one of the pages. Really, this is a pretty simple idea. It's not completely new in statistics. I would say that small sample census theory has some element to this, but it's not been yet realized as kind of how general this idea is. So in some sense, it looks like bias correction. But we're not trying to just correct the bias of an estimator. We're trying to get a confidence interval under biased data. So that's a little bit different. All right, so what we do is we identify what we call a rectifier. It is a quantity which is a population quantity. All right, it is the bias in some estimator. So I have some truth, theta star. I have some estimator, theta twiddle, f. And if I had infinite data, there would maybe still be a difference between the two of those. That would be a bias. Let's call that the rectifier. If I knew the population distribution, I could compute that. Okay? I don't know that, but I could try to estimate that. Now, in the bootstrap, you do something like this. You estimate the bias with bootstrap. Usually, bootstrap is thought of as estimating variance, but you can also estimate bias. It's another population quantity. You can estimate it, and you could correct. And that's done in bootstrap bias correction. We're not doing that, but it's not unrelated to that. We are going to make an estimate of this bias. All right, then what we're going to do is we're going to put a confidence set on the rectifier. Okay, the rectifier is a population quantity. As any population quantity, we can put a confidence set on it with our new technology, our fancy new conformal or whatever. And we can guarantee that I cover the rectifier with 95%. All right, that's possible. Using older technology and some of the modern things as well. Now that you have a confidence set on the rectifier, you can go back to the original prediction and use the confidence set on the rectifier to bias correct in a confidence interval sense the original point estimate. I can get a point estimate now for the bias corrections. So I can get a new set over here, this green set we call CPP. It's a confidence set that is based on the predictions, and it's based on the rectifier under which the predictions are wrong. It's based on a confidence interval for that. Okay, so that's it. That's the idea. I think I've written down some example of doing this to show how it relates to gradient methods. All right, so here is a little calculation where we're doing this for convex estimation problems. So we have a M estimator, convex loss, and we can calculate its gradient or the score function right there. And we can build confidence sets on that as the solution to these estimating equations. And so we can do a little decomposition. We can say that the expectation of, we'd like that estimating equation to be true, so we can write it out with these two pieces. The first one is an estimate of this score function just using the predictions, and the other is exactly the rectifier in this particular situation. Difference of expectations of score functions. That object we can build a confidence set on using off-the-shelf concentration inequalities or bootstrap or conformal or whatever. And then we have a theorem which says if you simply now take the confidence CPP to be the set of all theta such that 0 is contained in that difference, the observed expectation minus this rectifier confidence set. So that's a set difference. There's a real number minus a set, so overall it's a set. And I take all points such that 0 is contained in that set. That is the recipe for defining this prediction-powered confidence interval, or not even an interval, it's a set. And with all that set up, we can now prove a theorem that says that even with very, very few assumptions here, and with a prediction entity which can be quite far off, you can still cover the truth with a certified probability. Okay, so I think I'm going to finish now. Let me just finish up with that slide. This is the thing running in practice. Again, the code is really straightforward. I really kind of hope, this is brand new work, it's just on the archive. We're doing more with it, but I really want this just to go into software. I mean, this is this much code. If you're going to run predictions on things, there's no reason not to do this. Okay, just like there's no reason not to do bootstrap or something. All right, so anyway, that's that pitch, and so again, let me return to the non-parametric nature of this, non-distribution-free and non-parametric. It's not making those assumptions, so it really is a perfect fit to this modern era of using machine learning predictions. All right. Okay, so that's that slide. Let me just finish with this slide and one more. The words on that slide are all familiar, I think, to this audience, but I guess my ongoing agenda item in life is to make sure that sort of all the engineers out there using machine learning ideas and software use these kind of words a lot more, instead of just using prediction and make money. And especially, again, for the younger people in the audience, don't just be hemmed in to kind of what everyone else is working on. Don't do that. Do it for a while maybe, but really try to orthogonalize yourself. Personally, for me, that's been economics. And 5 years ago, I knew nothing. I knew fixed point theory or something. I knew some mathematics. Once you know some mathematics, you can pick up econ textbooks and just sail through them. It's so much fun. Stochastic processes and statistic, econometrics things. If you know all those, it's just like reading a novel. And it's really amazing thinking in those books. Just all the incentive structure, I kind of knew about it roughly, but to really see it in its home terrain in action, it's been super revealing for me. And that took about 3 years. Put it back next to your bed and read it when you have nothing else to do. Don't look at TikTok instead. Read econ books. All right. So anyway, that's my little personal sojourn. And let me just finish up with that, leaving that slide up there again. My father was a chemical engineer. He was actually at MIT as a master's student. And I didn't get really ever to talk to him about this very much. But once I started to kind of perceive that we are building a new engineering field and we're doing it with not knowing what we're really doing, and we're trying things out and all, I thought, the chemical engineers must have done that. And that is really true. In the 50s, that was the cool thing to do. That was the AI of the era, to be a chemical engineer. And they changed the world. They made so many products that would change our lives so much. And they were excited. They knew they were going to do that. But it was a big mess. And I just don't think they had the hype, though, that we have now. And they did have quantum physics behind it. We don't quite have that. So we're even less licensed to kind of get into all this hype. But anyway, it is worth looking at the history of how these things developed. Mathematics and science is important, but engineering is extremely important. These fields, civil, mechanical, have changed our lives more than anything else I can think of. And we do have a new engineering field emerging. I don't have a name for it. I don't think AI is a good one. I don't know what it should be called. Cybernetics was the MIT name that was used in the 50s. Not a bad name, but it's not going to catch on. But it is a field that is about data, it is about algorithms, it is about error bars and predictions and all that. But mostly it's about human values and utilities and decisions in collectives. And that's why the econ people are critically needed to partner. But again, they're not enough. We've got to do yet more. Okay, thank you.
Thank you, Mike. We can take a few questions. Don't be shy. Must have been crystal clear. Questions about the equations.
They're intimidated.
Yeah, Ali.
On the first part, is there an equivalent of the virtual types a la Myerson's theory for
Revenue
maximization?
So virtual types, I think it's auction theory. It's optimal auctions. And auctions are about Bayes-Nash equilibria, fundamentally. And Myerson's theorem tells you that, as you're having this little Bayes-Nash equilibrium among a bunch of auction participants, I'm the designer, I want to get high revenue out of it. That's great. Here, it's more this asymmetry. Even just one principal and one agent is enough. An auction with one person is not so interesting, and so it's a Stackelberg game. It really is a Stackelberg game. So we're trying to find Stackelberg solutions under uncertainty. Now we can have multiple agents, and we can get auctions meet Stackelberg, meet contracts, and that's I know not enough. I need to learn much more about that. Absolutely, some notion of virtual values will come in, no question. That's a way of discounting. But we need more Myerson theories, and again, a lot of them exist in economics. I really, just like I had a lot of respect for statistics when I was first learning, I said everything's already there. I kind of feel that way about economics, but again, when I look into the details, I say, wait, it's not ready for prime time. It doesn't actually update repeatedly over time with lots of data. It doesn't do hierarchical modeling. It doesn't do natural things that as a learning person I just will want to do in most problems. Maybe another way to say this: recommendation systems have had a huge, $1 trillion impact on our economy. They're critically important going forward. How do you help people make decisions by using other people's decisions? It's been done as a predictive engine, right? You don't see recommendations in economics textbooks. They should be integrated into all the decision making that economics people are making, and they're not. And that to me is a huge opportunity. There are people definitely working on it, probably in this room. But for the young people in the room, do a matching market with recommendations on both sides of the market. Okay, what if it's a matching market where I've got 100 million people here and I got 100 million people here? It's a huge matching market, restaurants and people or something, right? A person here cannot write down a preference list on everybody over here and vice versa. It's impossible, right? And they can't run a bandit algorithm trying out all options. The only solution is they get a little bit of a prior from other people in their social network on both sides of the market. And as those things run, then the matching is occurring. It's all happening organically. That's a thing. That should be worked on.